Exploring compound interest.
So if you are not one of my actual students, but you are a student at Johnson High School and you are watching the videos that I'm putting together for the distance learning, this is an activity that I call an exploration. My classes would do these about weekly, if not every other week they would do one. The intention of these is to give you an opportunity to figure out what a topic is before I actually teach it. It gives you a chance to come up with some ideas, and then ideally, the ideal situation would be is that you understand the content, but if you don't, at least it creates a basis for understanding. So, first point, if you have not printed this out and already begun to try and answer problems on here, go ahead, pause the video, print this paper out, start reading all the way through problem number one, at least. Go as far as you can, but at least through problem number one, and have an answer. All right, hopefully you feel confident about where you've placed all of these numbers into the formulas, and this is what it's going to look like. There's actually two problems there, so there's the one with the 10. You can have your principal out front, 6,500. You have the 1 plus your decimal form for your percentage raised to the 5th. And then this one is basically the same thing, but raised to the 10th power. I did do one thing that was different in the middle, which is go ahead and add those together. So it's kind of unnecessary to put plus point all that when you can just put the 0.035. So I wanted to show you one of each so you'd understand that one. Next, what we do, we just do the calculations. That's it. Just got to get my calculator set here real quick. There we go. Okay, so for the first, if you don't have a graphing calculator, you can actually just do these as individual steps. And what you would end up doing is taking what is in the parentheses and raise it to the 5th power. If that requires you to multiply by itself 5 times, then you just have to do that. Then the last part will be multiplying by the 6,500. So be aware that if you're doing it as individual steps, it begins with the parentheses, then the exponent, and finally the principal gets multiplied by it. There are apps out there that look like TI calculators that you can download, and then you can also go online to like Desmos, and you can do that stuff too. So it might be easier if you just have that open. All right, so calculate. I'm gonna, after 5 years, I'm gonna end up with that amount. I'll just copy that down. That is $7,719.96. That's what you get. Okay, so then the other one, back over there where the lighting's a bit better. You're gonna get a little over 9,000. Okay, there you are. All right, and again, as I go through the problems here, if at any point you have not answered a question that I'm about to answer, you can go ahead and pause and think about that problem, because that's the idea of this. It's not to give you notes and then later give you practice. It's that the practice is the notes and you're trying to figure out certain things. Okay, so I have this question here. Does the amount in the account double from 5 years to 10 years? Right? Did it actually double from here to there? Well, the answer is no. It didn't. It didn't end up being around like $14,000. Didn't make that transition. But maybe even more important of something else to kind of address here, and I'll come back to answering the rest of that in a minute, is if I took that number, see if I can pull these up. Okay, if I take that number and I subtract what was my original investment, I'm gonna get that amount, right? I'm gonna get that amount. So this is the interest that was gained over 5 years. You gained around $1,200. Okay, now let me double that, and I get $2,400. And I ask the question, if I add that, if I treat that as the interest and add it onto $6,500, then what I'm trying to do here is pretend, well, if I know the interest for 5 years, then the interest for 10 years is going to be the same amount. So I'll just add it twice onto that. And then we'll do a comparison, and we'll notice that they're not the same. They're kind of close-ish. I don't know. I mean, a couple $100, I guess, is a significant amount of difference there. Okay, so I wanted to highlight that as well, that because obviously that one's not twice what this number is, but if you take out that initial investment, you get closer to seeing that it's getting there, but it isn't. The reason that it's not is because if it was, what type of function would you expect this to go? No, that would be linear. That would be linear, a constant rate of change. And that's not what we're doing here. We're doing exponentials. Our variable is up here in the power. And a linear function, if you expect it to grow by the same amount over time, is just a straight line graph. But that's not what we have. We have an exponential type growth. In our case, because it wasn't a huge jump in those 5 years, we're around in this area where you don't quite see as much of an increase, but it does have a bend to the graph, which means that you're not going to have any constant change. All right, if you've not read any more beyond this point, go ahead and read some. Maybe you could do 3 and 4. When you have a bank account, interest is not calculated just once a year, right? You can go to your bank account and you can put money in, and you can take money out and put money back in. I mean, as you get paid, or your parents get paid and then put money in. So there has to be a system that you're not just calculating interest at the end of 1 year. You should be able to add more money in and take it out and always be able to check. So that gets us into this the real concept of compound interest, that you can compound more than once a year. So what we're going to do is explore some select amounts of time that you could compound within a year. Then eventually all of that is still going to continue into the thoughts and the idea of what our banks are really going to do. But now we need to go through this step. So this is the compound interest formula. You still have your principal, you still have the 1 plus, you still got your rate, and you still got your time in the same places, but now there's this value of n. And that value of n is going to represent the number of times, the times per year, that rate is calculated. So if we're going to calculate the rate, say, twice a year, what we're going to do is divide that rate by 2. So instead of using maybe 6%, we're only going to use 3%. But then to balance the fact that we did cut that, we're then going to double up the amount of time. So if you look real close, the operations are slightly different than each other in how we like divide, and then we do an exponent, but it does work. The mathematics in this does work. Okay, so what we're going to look at before we do any problems are just the common terms that we use to represent different values of n. So if we were just to say that it's going to compound annually, that means that your n value is a 1. And if you're to put a 1 here and there, the 1s wouldn't do anything, and it would get you back to the formula that's given to you way at the very beginning of the activity. Semiannual means that it compounds twice a year. So that means that n equals 2. Quarterly, n equals 4. Monthly, n equals 12. Daily, big number here, 365. Yes, technically 365 is not the number of days in a year, but we're just going to roll with it. All right, and then I thought I'd throw in a funny one here, which is bimonthly, because if you haven't heard of these things where it's like bimonthly, biweekly, by anything, that means that it takes 2 months or 2 of whatever it is to happen. So if it's going to take 2 months, and you divide the 12 months that we have in a year into groups of 2, that actually means that n is equal to 6. We don't use that one much, but I thought it'd be a good moment to share that one with you there. Okay, so question 4, we still have the $6,500. We're still going to let this go for 5 years at a rate of 3.5%. So everything is the same as what we saw in problem 1, but since we were going to compound quarterly, that means that you have an n value of 4. So then your formula looks like this. Okay, and then to save just a bit of time here, I've already typed it into the calculator, so I can just press enter. Oh, turned off on me, but I can just press enter. Oh, by the way, I did just put a 20 up there because, you know, do a little mental math on your own. 4 times 5 is 20. Okay, press enter, and you get 77.37 and about 21 cents. All right, now let's take a look. So the exponent was really big, right? It was 20 versus the 5, but you also had the dividing by the 4 down here. So let's do a quick comparison of that one versus what we got when it was annually. So 77.37 versus 77.19. So it's a difference of about $20, give or take there, right? Okay, so not too much difference. Just a different way of calculating so that it's not compounded only once a year. All right, next two questions, 5 and 6. We're gonna have you do 5 with monthly. So think about what number you're gonna use for the end value there. Try it out if you haven't already. And 6, just make a comparison looking at 1 and 4, which we already did. Look at 5 and then, you know, read the rest of that and see what you can answer from there. All right, let's take a look at number 5 and 6. In 5, you're going to compound monthly. That means that your end value is going to be a 12. So this is what your formula could look like. The n on the bottom there is 12. The 60, again, I went ahead and just multiplied because 5 times 12 is not a hard number to calculate. And I went ahead and already typed it into the calculator, so you don't have to watch me do that. Just press enter and we get 77.41 and 12 cents. All right, so that's what we get for monthly. All right, then question number 6. I think this is an important one for us to understand, like what's happening, and it gets close to an idea that we discussed in rational functions. So let that be sort of a hint there, rational functions. Not quite, but it's close to this idea. Okay, 6. Looking at problems number 1, 4, and 5. How is it affected? How does the number of times affect the compounding that we have there? So in problem number 1, whoops, it's on this page here. Still left that one as it was. Okay, sorry about that. All right, problem number 1 is, don't worry about the change. You've got 77.19, right? All right, and then when you compound quarterly with a 4, you get 77.37. So the number has increased, and it's increased by about 18. I think it said 20 earlier, but it's about 18 is what it increases by. Okay, so then when you do monthly, so now the 4 has changed all the way to a 12. It has continued to go up, right? It went from 77.19 to 77.37 to now 77.41. So the first observation should be the bigger the end value, the more you're going to get back in return. Okay. So that's what I wrote here in the first part. The bigger the end value, I just put equal sign, bigger n equals a higher output, A of t. We can expect that. But there's a little catch in here that I think is really important too. That as that number gets larger and larger and larger, this doesn't go out of control bigger, right? When you change to quarterly, you gained 18, which got you up to 77.37. Now that you went up to monthly, it's only increased this time by an extra 4. That was it. So just to really give you a concept here, I'm going to type in what you would get if you did this yearly. Or sorry, not yearly, daily. 365. Now I don't know the math for that, so I'll do 5 times 365. So a really large number. We're going to get back something bigger than this, but it's not going to be way bigger than that. You get 7,743. So now going from monthly to daily, it's only increased by about 2. So there's a complex idea here that the bigger the n, the more you're going to get back. However, you're going to be getting back less each time. So this is sort of like the idea from rational functions called asymptotes. Now, I'm not saying that it is an asymptote. I'm just saying that that thing that it's getting closer to an amount of interest. Like it's starting to level off at some number that we'll actually get. So problem 7 is an interesting question because we're not giving you all this information then asking you to calculate what the balance is going to be in the end, but instead we're asking you to figure out what the rate is going to be. In addition to that, though, what makes this one even more kind of interesting and challenging is that you don't know what the initial balance was. You don't have a principal amount. Instead, or a final answer either, what they do is they just say that that principal amount's going to double. Okay, so here's everything that I do have filled in so far. I know that my end value, because of the monthly, is going to be a 12. Also have a 12 up here. Also have a 14, and that's going to multiply to give you 168, which you'll see me do in just a bit here. But I don't know the p-value, right? So I got two variables, and I also don't even know what's going on over here. However, it does say that the value is going to double. So whatever my principal is, like if it were $100, it becomes 200, or 500 becomes 1,000. I can actually just describe it as 2p, right? Whatever it is, it's going to get doubled in there. And then when you start to do the problem here, and our objective is to get the R value by itself, we sort of chip away everything that we can. The parentheses, you're going to have to wait till the end. The exponent's tightly connected to that. The most outside piece here is actually going to be that principal value. And you would divide that out at the beginning. So if I had a number here and I had one there, I would actually divide them. But look what happens when we divide both of the sides by p. The p's cancel on both of the sides, and you end up with just 2 is equal to all this stuff. I'll go ahead and write that 168 there as well. So interesting thing here is that, and what we learned from that, if you really spend some time to concentrate on it, is that the amount of time that it takes to double an investment has nothing to do what the investment is at the beginning. It's just if you have a small investment, it's only going to double by that small amount, or if you have a large one, it doubles by the large one. But it really doesn't matter what it is, and that's demonstrated here in the very first step. Okay, for solving, this next step is going to be the craziest looking one. You have to undo this exponent, and the only way to undo that one is to use the root of that exponent. It's the same thing as a reciprocal, if you remember that business, but in the calculator, what you're going to end up typing is the 168th root of 2. Yeah, it looks crazy, right? But that's actually just what it is. So I'm going to take, I've got to remember how to do this on my calculator here. I'm going to use, see if you can see that feature there. Okay, so that allows me, oh, I typed the wrong one. All right, it allows me, at least I can work around it, to type in whatever index that I want. So I take the 168th root of that, and I'm going to get 1.00413. I might just need to keep that noted here. Okay, so I get 1.00413, etc., and that's equal to all this stuff that's up at the top. Oh, sorry, the exponent's gone, so it's just that part. And our objective here is to get the R value, right? So what now we're going to do, and you don't need the parentheses, I just wrote them because I was thinking I needed my exponent for a moment. You're going to then just subtract that 1, so the 1's going to disappear from the number that we see here, but I'll just do it. Minus the 1. You do need to do it, but I'll go ahead and show you. I subtract that, and that's going to leave us with the R over the 12. So then if we multiply by 12 to undo the division part, we end up with this number, that R is equal to 0.0496. Change that into a percentage number. You're going to shift the decimal over 2 spots, and you're going to get what's basically 5%. Okay? You're going to get that number. All right, when problem number 8 was added to the worksheet, I wasn't too confident in how much sense that it would make, but kind of reminded myself that I'd be going through this video and sharing with you ideas, and figured, okay, well, we'll try it out. Maybe some of you will actually Google this and learn a little bit from there. But I pose it this way anyhow. I give you a formula for it. Okay, I give you a formula for effective rate. So that's the capital R. I give you that formula, and I just want you to run a calculation. So if you had a percentage of 6.5, which as a decimal is 0.065, go ahead and plug that in for the R value, and then whatever my N values are, plug those in. So you're doing 3 different problems here. You plug them in and just run the calculations and see what you get. Now the first, that one's, when you plug the ones in for the end, they don't really do anything, right? So that one just cancels out with the other one and you get back to 0.065. Okay, so the others, it might take me a sec here to type them all in, but we're gonna have in parentheses 1 plus 0.065 divided by 4, raise that to the 4th power, and then subtract 1. No, didn't type it in correctly there. All right, let me try that again. Delete that. Get it in there. -1. Okay, didn't get it all in there that time. I knew that number was way too big. Okay, so you get this, right? And it looks, there's a lot of 6's in there, but it's going to give you 0.0666 and then 0.1. So we can just, actually, let me just stop. No, that's okay. I'll leave that one there. And then over in the first one, because there weren't any other numbers, it'd be like there's a 0 there. Okay, so the last one. I'll just recall what I typed up before. And we were changing these to 12s. And again, we don't know what we're doing right now. We're just calculating some numbers. But you do get 0.06697 if I wanted to go that far. So let's keep it at 4 decimals. So that'll be a 70. That's what we're looking at there. Okay, so now that that's done, and we don't know what we did, the next question is going to ask you, hey, what do you think this means? These numbers are actually fairly close to each other, right? That one's the actual interest rate that we had. Over here, it goes up by just a little bit, like 1/10, and well, whatever you want to describe. It's just barely higher than that one. And then that one's also getting just a little bit higher than it was. And what I hope that that reminds you of, let's see if I can find it. This question here, number 6, like how things in the balances changed as you increase the end values. And I don't know if I used the same numbers here, but I was showing an increase from just having a 1, maybe to quarterly to monthly, same thing. So you're getting more out of it there. What this actually is, this is the interest rate that you actually sense, that you feel. So something can be advertised as 6.5%. If it's compounded annually, that's what it is. But if it's compounded quarterly, you actually feel it as if it's 6.66%. And if it's compounded monthly, the way that you feel that is as if it were a 6.7%. So the effective, kind of think of that word there, the effective rate is what's actually going to happen when all this is said and done. So even though we call it 6.5, it's what we get out of it. Now, reminder, well, I never mentioned this before, but I'll throw it out there. I've been talking about this as if it's your bank account and if you're investing money. And you should be thinking, yeah, let's compound as many times as we can. Remember that there's another end, that banks, when they loan out money, it's just the opposite. When a bank loans out money, and you don't want it to be compounded at a higher amount because that means you're going to pay more. But that's just how the system is. And but anyway, good little perspective on how that's compared as. Okay, so number 1 I just wrote, or number 9 I wrote, yeah, it's the actual interest rate for the year. It's the way that you feel it, the way that you sense that actual change there. Okay, question number 10, just to follow up on that one. You got a guy, Arturo, that he has a choice between a couple different accounts. It's kind of interesting here is that the first, well, they're advertised at different percentages, right? So you get 2.5%, you get 2.48%. 2.48% is actually just a little bit less than this one, right? So if this is going to be money, and it's about perspective, so I'm glad that I mentioned that just before, about perspective. If he is going to put money into an account, that one looks better to start with. If he's taking a loan, that's the other perspective, right? And you'd want that one. But right now he's trying to invest money into something, so that one seems better. But in the details, one of them is compounded quarterly, the one that looks better, and then the other one is compounded monthly, right? So what you need to do then is run this final calculation on the effective rate. Let's get those percentages in. let's do the compounding correctly, and let's see which one turns out to be bigger. Now I'm gonna stop the video here because I'm gonna let you just do that part on your own. Okay, but find out which one's better. They're not gonna be that different from each other, but one of them's gonna be slight better, and you want the one that is bigger because he is depositing money. Okay, you want the one that's bigger because he wants more return on that.